This is the first of 4 lectures dealing with geometry. Its title is Geometry in History, and we'll look at the development of geometry. Geometry began with a practical need to measure shapes. The word geometry literally means to measure the earth, geo being earth. And we go back to ancient Egypt, and it is said that geometry became important when the Pharaoh, at the time, the leader of Egypt, wanted to tax the farmers who raised crops along the Nile. The Pharaoh's name was Sesostris, and he ruled that the land had been given to the farmers by the gods. And of course, the Pharaoh was one of the gods. In fact, he was the only god around to pay a tax to. And since the gods had given this land to the people, and the gods had caused the Nile to spill over its banks, bringing rich soil from the central part of Africa to these farmers' fields to enhance the yield of crops, it was only fair that the farmers, who were becoming rich, gave some of that wealth back to the gods. And since the only god around, again, was the Pharaoh, he would collect their payments. The question was how to compute the correct amount of tax based on the shape of the land and the amount of land the farmer had. The government agents had to be able to measure these various shapes of the land to compute the taxes. So, we had to create some mathematics. And the beginnings of computational geometry was there, right then and there. Humans had certain understandings about shape well into the past prior to the Egyptian civilization. But the Egyptians made a science out of this, and starting with those Egyptians to nowadays, we have the development of geometry, an opportunity to study size and shape and relationships. Okay, as civilization developed, geometry became more complex. Around 2900 BC, quite a few years ago, the first Egyptian pyramid was constructed. Knowledge of geometry was vital to those who directed this construction. The earliest record of a formula for the area of a triangle indicates that the Babylonians accomplished that in 2000 BC. Knowledge of angle measures, something we study in school, is critical if a sundial is to provide accurate information about the time of day. There is evidence that the Egyptians had sundials as early as 1500 BC. And looking at the sundial, you can see that you had to understand the placement of the sun and the angle with the device that provided the shadow that allowed you to tell time. It is believed that the knowledge of geometry and geometric principles was developing in ancient India and China, but no records exist to prove this. The problem was Chinese and Indian scholars wrote on materials that have decayed over time. The Egyptians and Babylonians left many records on clay, and of course clay lasts a long, long time. Part of the problem with deciphering these clay tablets was understanding the language. And for example, much was not known about the Babylonians until they were able to find a tablet that had Babylonian writing, that is the cuneiform writing, as well as a language that was known. The same happened with the Egyptian hieroglyphics. It could not be translated until we found, I believe it was the Rosetta Stone, which was found by a member of Napoleon's army when he invaded Egypt, that allowed us to translate hieroglyphics, because in addition to the hieroglyphics, there were also writings in ancient Greek, a language that, of course, was well known. In the Greek world, the ancient Greek world, there were 3 philosophers, 3 great philosophers, whose works in geometry are still studied today. The first was Thales. Thales was the first really great geometer. He lived in Egypt and in Greece during the 6th century BC. He was also considered a statesman, an engineer, a businessman, and an astronomer. In other words, he was a very busy fellow, and actually was a very brilliant fellow. His ability as a problem solver was demonstrated when King Croesus of Lydia needed a bridge constructed to allow his army to cross a river in pursuit of an enemy force. The king was in a hurry and called upon Thales to find a solution, or else, I guess. Thales had the soldiers dig a canal to divert the river's waters, which allowed the army to walk across the dry riverbed, which was a lot quicker than building a bridge. It is said that after the army had crossed the dry riverbed, Thales demanded that the channel be refilled with soil so that the river could once again flow on its original path. Thales studied similar triangles and wrote the proof that corresponding sides of similar triangles are in proportion. In a later lecture, we will address similar triangles. It is written that Thales' knowledge of astronomy caused him to predict a solar eclipse. Remember that one's knowledge of astronomy had a great deal of mathematics in it, certainly in those days and certainly today. So he applied his mathematics to astronomy and predicted a solar eclipse that is believed by modern scientists to have occurred on May 28th, 585 BC. There's a great significance to that date. No, it is not my birthday, nor is it the birthday of anybody I know, because they'd be pretty old if they were born May 28, 585 BC. But we do know that there was a battle that took place that day between the armies of Lydia and Medea. And the battle was halted because of the solar eclipse. The soldiers feared that this eclipse was an evil omen, and both armies packed up and went home. What is significant about this is, since we know the date of the eclipse, and because it was predicted by Thales, and we know the event, this is the earliest known historical event for which we have a precise date. That's quite significant. And again, it was strictly due to Thales' ability to predict a solar eclipse based on the very early knowledge of geometry and other mathematics that was available at that time. Probably, in terms of mathematics, the most significant contribution that Thales produced is that he is given credit for the development of the deductive process or deductive procedures. This is a process still taught in school today. If you take a geometry course in high school, you are generally required to prove things. Given this and given that, prove two triangles are congruent. Prove that the radius is perpendicular to this chord, or whatever it is. The idea is that process goes back to Thales in the 6th century BC. The next great Greek geometer was Pythagoras, a name we've heard before. Pythagoras lived also in the 6th century. It is thought that Pythagoras studied under Thales. Unfortunately, little is known about Pythagoras as a person. In fact, there are some scholars who believe that Pythagoras never existed. He was just an artificial person created to have all this great knowledge. Pythagoras founded a brotherhood called the Pythagoreans that pursued knowledge in mathematics, science, and philosophy. The Pythagoreans developed properties of parallel lines, proportions, and similar figures. The Pythagoreans produced a musical scale by relating the length of a string on a lyre to the pitch produced by plucking that string. Experimentation with bells and containers of water verified the proportional relationship. And there today in music is a Pythagorean scale, relating mathematics, relating geometry to sound and the pleasure of sound we call music. Probably the most famous contribution of the Pythagoreans was the Pythagorean theorem, something, again, everybody is exposed to during their normal education. The Pythagorean theorem says that the sum of the squares of the two legs of a right triangle, the legs are the two sides that make up the right angle, that sum is equal to the square of the hypotenuse being the side opposite the right angle. We know that the builders of the ancient Egyptian pyramids knew about this. How do we know that? Well, the fact is that we know that they used a 3-4-5 right triangle to make right angles. Found in the ruins of some pyramids was a piece of rope with knots, one knot at the beginning and then 11 more knots and a 13th knot at the other end of the rope. And it was believed that this knotted rope was used to form a right triangle, a 3-4-5 right triangle, because if you formed that 3-4-5 triangle, you knew that it was a right angle, and therefore you could make sure that the corners of the pyramid were at right angles. We know that the Chinese understood the relationship that we call the Pythagorean theorem as early as 1000 BC. Now, wait a second. You said 1000 BC was hundreds of years before Pythagoras allegedly lived. Yet we call it the Pythagorean theorem. We don't call it some Chinese name. And like in many other things in mathematics, Pythagoras gets the credit. And I'm not sure in parts of China if they call it the Pythagorean theorem or they have a Chinese name based on some possibly mythical Chinese mathematician who worked hundreds of years before Pythagoras. There have been a number of different proofs of the Pythagorean theorem. Perhaps the most unexpected source of a proof was James Garfield. Garfield was a president of the United States. In fact, he's one of the 4 presidents who was assassinated while in office. And Garfield used a trapezoid, a figure we'll talk about in a future lecture, to prove the Pythagorean theorem. The proof was accepted, and of course, he had done this many years before he got actively involved in politics. I would challenge most politicians today to come up with a unique proof of some important mathematical theorem. Euclid is the third of the 3 great geometers. Euclid was a Greek who lived in the area about 300 BC and is considered the father of geometry. He wrote a book called The Elements, a text which covered all the knowledge about geometry, number theory, and algebra that existed at that time. In fact, if Euclid came alive today and walked into a geometry classroom in a high school and could understand English, he would understand everything the class was doing and probably point out to the teacher and the students that he should have a royalty on that book because he originally wrote all that material down in his book, The Elements. Euclid's goal was to present an organized work that emphasized deductive reasoning, again, the kind of reasoning that was influenced or created by Thales. He established a few basic postulates whose truth was accepted. From this beginning, theorems were proven using the postulates and eventually using previously proven theorems. And this is exactly what one does in a geometry class. The deductive process is called the Euclidean process and is used in all branches of mathematics. The geometry that is studied in high school today, as I've said, is exactly what Euclid created. Very little has been done in the area of geometry in terms of what's in a high school class that was not created by Euclid. There are more modern geometries beyond Euclid, but they generally are studied at the college or graduate school level. Work in geometry was conducted on an isolated basis for hundreds of years after Euclid. Much of the knowledge that was known in the 4th century BC was lost and had to be rediscovered. Why was it lost? Because, again, the works were generally kept in Alexandria, and if you didn't have access to Alexandria in Egypt, you had no way of getting a copy because the printing press was a long way from being invented. So we had Europeans who had no access to this, quote, forgotten knowledge, the knowledge of geometry that was known to the ancients in Greece and Egypt. Now, what happened in the meantime? What happened in the meantime is people, in effect, had very little opportunity to advance in science because they didn't have the mathematics, especially the geometry, they needed. And there was no opportunity to learn it. Again, the people that created this, Thales, Pythagoras, Euclid, were brilliant individuals in many areas as well as besides mathematics. And obviously, for hundreds of years thereafter, brilliant individuals of their ability did not exist to rediscover what those gentlemen knew. When Arab armies conquered North Africa and absorbed the learning that was found in Alexandria, they spread a lot of this learning. They invaded India, and as we had seen, they took information from India, but they also provided information to scholars in India, information that had been kept in the library in Alexandria. The Indians had some work being done in geometry as well as arithmetic. Brahmagupta, an Indian mathematician who we earlier mentioned, in 628 studied the sides and the diagonals of various polygons. And polygons is a subject of a future lecture. So The influence of knowledge coming out of Alexandria was felt in India, and work was being done. The wars and trade between Europe and the Muslim world caused the knowledge of the ancient world, the knowledge of geometry, and the knowledge developed in North Africa, in Muslim Spain, and in India to be transported to European centers of scholarship at a very slow rate of speed. Because in many cases they weren't trading, they were fighting. The rebirth of academic pursuits in Europe ignited a search for geometric knowledge. In 1260, a Latin translation of Euclid's Elements became a text at universities located in major European cities. The development of art during the 15th century, which is called the Renaissance, required an understanding of geometric perspective. Paintings had to show depth, and knowledge of proportion was vital. We see here a painting by Da Vinci. Leonardo da Vinci was a great mathematician as well as a wonderful artist, and he is given credit for advancement of the use of geometry in painting to make those paintings appear to be real, to be photographic. In 1453, Arab armies conquered Constantinople, the last bastion of Rome in the east. Greeks who fled the city of Constantinople relocated to Italy and brought with them their knowledge of ancient Greek mathematics. Again, these people had been isolated from the rest of Europe for hundreds of years, and now the knowledge came to the centers of civilization, primarily in Italy. The invention of the printing press allowed knowledge of geometry to spread rapidly. René Descartes, a name we've mentioned many times, was dissatisfied with the ancient thought that he had been taught while studying at the University of Poitiers. He sought to create a new philosophy. Descartes believed that the universe was created with a divine mathematical plan. His philosophy maintained that the laws of nature could not be varied. He believed that all geometric relationships could be described mathematically. Let's see what that means. That means if you had an arithmetic or algebraic relationship, you could portray that relationship with a geometrical form. And we've talked about this in terms of the importance of Descartes, in terms of taking algebraic functions and being able to graph them. The word graph means to picture. And of course, his ability to do that required him, in effect, to create what is called the Cartesian plane. And here we have a picture of the Cartesian plane with points indicated with ordered pairs. We'll recall that the ordered pairs are like latitude and longitude in terms of using numbers to locate a unique point. Let us look at the points on this coordinate plane. First, before we do that, let's recognize we have the x, the horizontal, and the y, the vertical axes, which intersect at the point 0, 0, called the origin. And of course, he was the first, that is Descartes, was the first to align these two number lines in a perpendicular fashion to create this plane to enable mathematicians to graph functions, which enable scientists to picture real-world occurrences that could be made into mathematical functions. And of course, again, the plane, as we mentioned earlier, the Cartesian plane is named after René Descartes, Cartesian being an adjective form of Descartes. Well, let's take a look at some of these points. And we see that there is a point that is located on the y-axis. That point is 0, 4. Ordered pairs are called ordered pairs because the order is important. The first number is the x coordinate. The second is the y coordinate. In fact, if we go to a three-dimensional graphing situation, where we have a graphing space rather than a plane, we'd have ordered triples, x, y, z, with commas in between each number. 0, 4 means we're on the y-axis because x is neither positive or negative. It's right there on the y-axis. And 4 means we are 4 units above the x-axis. Rotating ourselves clockwise, we come to a point labeled 3, 2. By the way, this is a fourth of the plane called a quadrant, which is bound by the x and y axes. And every coordinate in that quadrant is positive. Both the x and the y are both positive. It is the only one of the four quadrants where the coordinates are both positive. And we say that's the first quadrant. And of course, 3, 2 means that we move 3 units to the right of the origin on the x-axis, and then 2 units up in the y vertical direction to come to that point. We are 3 units from the y-axis and 2 units above the x-axis. Continuing our clockwise motion, we come to a point labeled 7, -3. Notice the x is positive, the y is negative. This is the only quadrant where the coordinates have a positive x and a negative y. And this is called the fourth quadrant, because when they numbered the quadrant originally, they went counterclockwise. So this is quadrant number 4, and 7, -3, is 7 units to the right of the y-axis and 3 units below. Continuing our clockwise motion, we come across a point labeled -1, -2. And this is in the third quadrant. In the third quadrant, all coordinates are negative, both the x and the y. Again, the only place where that occurs is the third quadrant. And -1, -2 is located 1 unit to the left of the y-axis and 2 units below the x-axis. Continuing our clockwise movement, we come to the x-axis and a point located on it, -6, 0. Notice our point on the y-axis had a 0 for x, followed by a non-zero number for y. On the x-axis, we have a value for x that is not 0 and a value for y that is. And this, of course, in terms of a curve or a line, would be the x-intercept. -6, 0, 6 to the left of the origin on the x-axis. And if we continued into the last quadrant, the second quadrant, located between the negative x-axis and the positive y-axis, we would come across coordinates that had a negative x and a positive y. In fact, this becomes quite important when we develop trigonometry as an algebraic function, but that's for another time. So we have the creation of the coordinate axes, the creation of the Cartesian plane, which we have seen earlier was used to visualize functions, to visualize the notion of the derivative, and to do many things that people could not do. So we see, looking at the history of geometry, you see some very frustrating times because knowledge existed but was not known to the people who needed it. The knowledge existed in Alexandria but was unknown to people in Europe who were working on problems who needed that information. So in a time of desperate economic situations, desperate intellectual situations, knowledge that might have helped was unavailable. And the question that might be asked, and I'm no historian, was the Dark Ages a cause of the lack of information, or was the lack of information a cause of the Dark Ages? I think it's a fascinating question because history, obviously, and mathematics are intertwined. Mathematics affects history, and history affects mathematics. Getting back to Descartes, he studied these geometric properties by using the coordinates in the plane, not only to study algebraic functions, but to study geometric shapes, because now we could quantify these shapes. For example, if you had a shape that had vertices, we could identify those vertices as ordered pairs in the Cartesian plane. If we were looking at circles, the center of the circle would be a point, and any point on the circle would be a point with given coordinates. And intersections of shapes, again, would occur at points which were coordinates on the Cartesian plane. So Descartes' work really gave birth to a great deal of opportunities for algebra, geometry, as well, of course, as calculus. And this is one of the reasons why in the typical school system approach to learning, at least in the United States, you take a geometry course. And then you should take something called analytic geometry as part of a pre-calculus course. Again, the intertwining of algebra and geometry to allow us to study change, the study of calculus. Descartes' final work was called Principia Philosophiae, which was published in 1649, a year before he died. It included his thoughts on mathematics, science, and astronomy. Again, until recent times, people who were mathematicians usually did other things, or people who did other things also were mathematicians. So whether Descartes was a mathematician, a philosopher, a scientist, or an astronomer cannot be discerned. We just simply say he's all of those. Today we'd find very few people who would have a vocation and say, my vocation is mathematics and science and music and philosophy. They would typically have one vocation, and possibly some of those things would be avocations. Let us go back, since we have some time, to our discussion of Pythagoras and the Pythagorean theorem. Because again, one of my most interesting areas for me in mathematics is sequences and patterns of those sequences. And the Pythagorean theorem led to a sequence of numbers called Pythagorean triples. We mentioned 3, 4, 5 as a Pythagorean triple, but that was not the only one. In fact, it turns out there's an infinite number of Pythagorean triples. We're going to look at a few of them and sort of generalize from those few to see how we could create an infinite number. Here you see 4 Pythagorean triples, one of which we've already looked at, 3, 4, 5. The next is 5, 12, 13. And then we have 7, 24, 25, and 8, 15, 17. Now, the first thing I would do as a mathematician looking at this would be to say, how are these sequences different? And the first thing you might say is, well, 3, 4, 5 have consecutive numbers. There's no number between 3 and 4, nor between 4 and 5. The same is not true for 5, 12, 13, or the other two. All right? Let's eliminate 3, 4, 5 and differentiate between 5, 12, 13, 7, 24, 25, and 8, 15, 17. You'll notice that in the 5, 12, 13, and 7, 24, 25, the second and third number are adjacent or consecutive numbers. While in 8, 15, 17, there is a separation of 2. There is a number, 16, between 15 and 17. Let's take a close look at 5, 12, 13. 5 squared is 25. 25 is 12 plus 13. In fact, any odd number, such as 25, can be obtained by adding 2 adjacent numbers, in this case 12 plus 13. So we start with a square odd number, 25. We recognize which 2 consecutive numbers sum to that number, 12 and 13. And we know that the difference between 12 squared and 13 squared is 12 plus 13. This is true for all square numbers. The difference between one square number and the next is the sum of the 2 bases. In this case, the difference between 12 squared and 13 squared is 12 plus 13. But 12 plus 13 is 25. So we have 5 squared plus 12 squared would equal 13 squared. And now all we need to do is find an odd square number, find the 2 consecutive numbers that add to that number, take the square root of our odd square number, and we have a Pythagorean triple. For example, 49. 49 is an odd square number. 7 squared is 49. 24 plus 25 is 49. And therefore, 7, 24, 25 is a Pythagorean triple. And there's an infinite number of those. But now the last one we're looking at, 8, 15, 17, is different. The difference between the 15 and the 17 is 2. We have a 16 in between. You might notice that if we add 15 plus 16 and 16 and 17, we get 64, which is 8 squared. If you'd like to investigate that further and find the pattern there, I leave it up to you. But there is a pattern, and again, we can create an infinite number of Pythagorean triples. So something was done more than 2,500 years ago can still be entertaining if you're interested in patterns and the recognition of patterns. Our next lecture, lecture number 14, will discuss geometric relations. We'll discuss area, volume, and relations in polygons.